Hi there, another quick pre-video discussion. I did not record this one properly. I have a way around it, but it's going to be kind of clunky, so this video is going to look kind of weird. Sorry about that. Alright, so this video might be a bit shorter here because we ended up doing a lot of recovering stuff in the last video, which ended up being like half an hour, so I'm leaving this as its own video if you want to just skip the new stuff, but because of my time constraints and all that, this might be a bit of a shorter one, but thankfully we just have one more chapter, sub-chapter thing here to cover anyway, so that's going to be this video here. And what that subchapter is a discussion of the diagonal map. I don't know what that is, so probably this one's going to be useful. So as always, set up, let G be a Lie algebra over K. It's going to be free as a K module. So the bracket structure might not be free, but everything else is. Definition. The Lie algebra homomorphism triangle from G, I'm changing my grip on the pen and it is causing me problems, from G to the product of two G's given by, you may have seen the diagonal map before, it's just sending an element X to two copies of itself. And this induces a homomorphism of associative algebras which we're also going to write as triangle. This is going from the universal algebra of G to the universal algebra of G twice, tensored with itself, as you might expect, which is going to be called the diagonal map. Alright, so, proposition. This diagonal map is characterized by two conditions. First off, it's an algebra homomorphism. And secondly, that the image from the element X in the universal algebra under this map is X tensor 1 plus 1 tensor X for all X in our original group. And that is, of course, being identified with the image of G inside of U of G. And this all is pretty clear since, as always, the base field and the image of G characterize the universal algebra. We get this for free. An element alpha in the universal algebra of G is called primitive Sorry, I'm holding the pen farther back because it should help with my hand with writing for so long, but I'm not used to writing like this. And it's called primitive if its image under the diagonal map is as if it was in G, essentially. So of course we have that all of G is primitive. All right, here is a theorem now. Assume that K is torsion free. I believe that means this is as a Z module. I believe that means as an integer module. And that G is a free K module. And then a set of primitives of the universal algebra G. What even happened there to that letter G? Coincides with just G itself. So essentially, we know that every element of G is primitive. We want to see that every primitive is an element of G, in this case. Now, first off, look at the case when G is abelian. You saw that, right? Like, part of the line just, like, vanished. We have that the universal algebra of G, in this case, is identified with the polynomial ring of corresponding indeterminates. With each capital Xi indeterminate corresponding to a basis element Xi of UG. Of G, sorry, not UG. So the diagonal map can be interpreted as a homomorphism in this case sending, normally its domain is UG, which in this case is the same thing as K of Xi, and sending them to, find it is the, normally the Cartesian product of the tensor product of two copies of UG, which under this identification is equivalent to two different copies of the sets of indeterminates, which are going to be distinct from both one another and those in the domain. Where the first one, these are equivalent to tensor 1, and of course vice versa in the other case. The double prime being 1 tensor Xi. And in this case, the diagonal map of a function f of xi prime xi double prime is equal to f of xi prime plus xi double prime, because it sends each xi to, or just both we write as xi prime plus xi double prime. Thus, the primitive elements f of x inside our polynomial ring are those where this sum essentially splits across f if f is additive like this, then so does, we can break this down into its homogeneous components which we write as f sub n, ff is homogeneous of degree n and additive, then we have this condition 2 to the n f of some xi being equal to f of 2xi being then split into the sum of each individual xi, which by additivity is just 2f xi. And this gives us that 2 to the n minus 2 of f is 0. Now, since k is torsion free in Z in the integers, we have f is equal to 0 when n is not equal to 1. So f is linear. All right. Now let's look in the general case. Our map delta from UG to the tensor of UG and UG induces the graded version of delta, which is a map from the graded universal algebra of G into the grade of course, UG tensor UG, which is the grade of the universal algebra of the direct sum of these two copies of G, which is, of course, the tensor of the individual graded universal algebras. Now, as we have that these graded universal algebra G's in this context are isomorphic to the symmetric algebra in G's and G, and the corresponding map from the symmetric algebra of G to the symmetric algebra of G tensor itself. I don't think this qualifier as is useful. Is as in the first case, where this reduces to this linear map. And that is by its effects on the elements of the first grade of the universal algebra. So we're going to let x be an element of u sub n of g with an image x bar in the nth grade of the universal algebra. If x is primitive, then x bar is primitive for the graded diagonal map. Hence, if n is greater than 1, then x bar, its image is 0 from above. But yes, because these are all abelian, right? Thus, we have x in u sub 1 of g as x is the sum of an element in k and an element in g. Then let's just go ahead and make a new page just for the hell of it. Diagonal map of x is equal to lambda plus y tensor 1 plus 1 tensor y with, and put this on the left, is just x tensor 1 plus 1 tensor x x plus y tensor 1 plus 1 tensor y. Thus, if x is primitive, we pick up an extra lambda here, I forgot, as we do this. Lambda is going to be 0, obviously. And x is in our g as desired. Bit of a shorter episode, but episode's a weird thing to call it, but that is the end of that discussion. Next time we're going back to our previous text to discuss representations. So looking forward to that. I didn't record any of that. Fuck. I know a way around that.